The pursuit of knowledge begins here. Welcome to Inquisitio. Imagine a place in space where all the known laws of physics simply cease to function. A point of such extreme density where time itself seems to stand still and from which not even light, the fastest thing in the universe, can escape. For decades, science treated these regions as mathematical anomalies, invisible scars on the fabric of spacetime. Today, however, we know they are not only real, but they are in command of almost everything we see in the night sky. At the heart of nearly every large galaxy in the universe lies a dark secret. This is not merely a hungry abyss consuming everything that ventures near. It is an invisible maestro whose gravity dictates the destiny of billions of stars. Many believe that supermassive black holes are purely destroyers, chaotic forces dedicated to cosmic annihilation. But modern astrophysics reveals a fascinating paradox. Without these gravitational monsters, the universe as we know it, the galaxies, and perhaps life itself, would never have existed. They are the silent architects of the cosmos. To comprehend the scale of this mystery, we must first look at our own cosmic home. At the center of the Milky Way, about 26,000 light-years from Earth, lies a region of chaos and absolute silence known as Sagittarius A star. For a long time, astronomers suspected that something massive was hidden there, but interstellar dust blocked our direct view. Confirmation came through an extraordinary indirect observation, one that eventually earned the Nobel Prize in Physics for the scientists who led it. They tracked the orbits of a group of giant stars inhabiting the galactic center. One of these stars, named S2, captured the world's attention. It orbited a central point that appeared completely empty. Yet, as it neared this void, the star accelerated to astonishing speeds, exceeding 24 million kilometers per hour, about 3% of the speed of light. To fling a giant star at such speed, that seemingly empty point would have to contain the mass of 4 million suns, compressed into a space smaller than our own solar system. There it was, our supermassive black hole. Unlike stellar black holes, which arise from the collapse of a single massive star at the end of its life, supermassive giants are true titans of incomprehensible scale. They possess millions to tens of billions of times the mass of our sun. Their origin dates back to the very dawn of time, shortly after the Big Bang, raising questions that challenge the limits of our science. How could something so immense form so quickly when the universe was still young? This is one of the deepest questions in modern cosmology. The answer to the existence of these giants may lie in how they evolve in perfect symbiosis with their host galaxies. In astrophysics, there is a direct and mysterious correlation known as the Magorian relation. It demonstrates that the mass of the central black hole is always proportionally linked to the mass of its galaxy's bulge. This means that the growth of the black hole and the growth of the galaxy are connected by a cosmic dance of mutual feedback. As the galaxy's gravity pulls gas and cosmic dust toward its center, the black hole feeds. However, this feast generates a colossal amount of energy. As it approaches the event horizon, matter does not fall directly into the abyss. It swirls around it, forming what is known as an accretion disk. Under the influence of extreme pressures and brutal gravitational forces, the gas in this disk is accelerated to significant fractions of the speed of light. Friction heats this material to temperatures of millions of degrees, emitting radiation so bright that it can outshine the light of all the stars in the galaxy combined. We are talking about quasars, the brightest beacons in the observable universe. In addition to this intense glow, the colossal magnetic fields generated by this rotation create relativistic jets, columns of plasma shot from the black hole's poles at speeds close to that of light, extending for thousands of light years into intergalactic space. This immense energy acts as a cosmic thermostat for the galaxy. When the supermassive black hole feeds too aggressively, the extreme heat and radiation push the remaining cold gas out of the galaxy's boundaries. Without this cold gas, the formation of new stars is abruptly halted. The architect, therefore, decides when the galaxy should grow and when it should fall silent. It is a dynamic and extremely delicate balance. If the black hole were less active, galaxies would produce stars uncontrollably until they quickly exhausted their fuel. If it were too active, it would sterilize the galaxy before stable planetary systems could even consolidate. But the role of creator coexists with its nature as an implacable devourer. Occasionally, the balance is broken. An unlucky star, orbiting deep within the galactic center, may have its trajectory altered by the gravity of other stars and be directed into the danger zone. When this star approaches the gravitational limit of the black hole, it experiences a phenomenon of pure destruction known scientifically as a tidal disruption event, or, more dramatically, spaghettification. The force of gravity exerted on the side of the star facing the black hole is immensely greater than the force exerted on the opposite side. The result is that the star is physically stretched until it takes on a filamentary shape, like a strand of pasta, before being completely torn apart. A portion of this stellar matter is flung into deep space, while the rest spirals toward the event horizon, releasing an intense glow of X-rays, the star's final cry of agony before eternal darkness. If an observer could watch this star falling toward the black hole from a safe distance, they would witness something bizarre due to the effects of general relativity. As the star approaches the boundary of the event horizon, time for it would appear to pass slower and slower relative to the observer's time. The light emitted by the star would begin to undergo an extreme gravitational redshift, becoming increasingly faint and red. To anyone watching from the outside, the star would appear to freeze in time right at the edge of the abyss, slowly fading into darkness, though for the star itself, the fall continues relentlessly toward the singularity. To look at a supermassive black hole is to contemplate the extreme limit of our own understanding of reality. They are the junctions where Einstein's immense gravity and the subatomic laws of quantum mechanics collide. But above all, they are a reminder that in the universe, destruction and creation are two sides of the same coin. The stability of our galaxy, the orbit of our solar system, and the very matter that makes up our bodies are, in a way, consequences of the architecture designed by these invisible giants inhabiting the cosmic dark. If this glimpse of the immensity and mysteries of the cosmos has awakened the desire to unravel the forces that govern our universe, join us on this journey of discovery. Subscribe to the channel to follow our next scientific explorations through space and time. Because here, curiosity never sleeps, and there is always more to discover.